Yeah, we're back here. For the past day, I've been chasing down what I thought was a huge error, but it turns out it's not really an error. It's just something I forgot to do. Well, let me one and show you here. Okay, here it's working. Right here, you can see everything. It's the autoencoder. It takes in an image, passes to the layers, and everything works fine. But here's something else. Okay, here. Right here, I'm using the Adam optimizer, but if I change it to, let's say, let's say momentum, basic momentum, and then run it again, something weird happens. As you can see, it just doesn't work anymore. Like I said, I just took the entire day trying to figure out why it wasn't working. And all the outputs, the output here is 1, then it's 1.7, 23. It just explodes completely. This is what you call exploding gradients. The Well, basically, gradients go out of bounds, and you get something that just doesn't make any sense. I mean, the network is still working, but the gradients are just out of bounds. And what it turns out to be that the Adaptive Optimizer is fixing it by just optimizing the gradients. It makes sure nothing goes out of bounds. And the Momentum Optimizer just doesn't do that. AlgoGuide, same thing. It just doesn't work as well. So the main cause is that the learning rate is way too high, but adjusting the learning rate is really not a good solution for this. So what we need is some way to constrain the gradients, constrains the weight so that they stay in bounds. But the basic solution is just to clip the weights, but that really doesn't work, because if you just clip the weights, then some of them are not going to be able to learn properly. So we need a way to nudge the weights into the direction that we want. Okay, so there's something called batch normalization I tried to do, but that one doesn't. It can work, but it's really complicated. You have to get into the structure of the neural network, and that would just take way too long to code, and it's basically impossible. I'm just not gonna do that. And I tried an instance normalization. That's easier, but it's still way too complicated. Instead, I'm going to do something. I'm going to try clipping the weights. No, not clipping them, but nudging them in the direction that they want. If you know something about if you know variational autoencoders, they do something about parameterization and the adding the normal standard deviation. But we're going to try to do something much simpler than that. But that gives us basically the same result. So I choose to do it right here in the backpropagation of the transfer function. I'm going to make a special function to do that, but actually, let's just do it now, because it's really tedious. Okay, let's just copy this. Oh no, wait. If I do this in here, it's I mean, let's just do it here just to demonstrate, and then we're gonna fix it later. Okay, first thing we're gonna do, we're gonna use a gradient that's relative to how far the weight, not the output, is from a certain range. Like if it's close to 0, we're gonna do nothing. But as it gets further and further away from 0, past 1, we're gonna push it. We'll push it inwards. So first we have to measure how far the thing is from 0, and then the further it is from 0, the more we push it back to 0. We need to be as close to the standard, the mean, as possible. Well, the mean here is 0, and the standard deviation 1, but we're not going to worry about those kind of details. That would just be way too complicated. Just know that the farther it is from 0, the more we add a correction to push it back towards 0. If it's close to 0, we do basically nothing. If it's far from 0, we push a lot. So now we're gonna figure out to do this. Okay. Now we need to figure out how far it is. Let's call that the gap. Okay. Okay, first thing you need to do about the vectors here. Well, first of all, it's a vector. The gradients is just a vector, and one thing about vectors, you can just add them together. So we just need to take a vector and add another vector to it. So if you make the push gradual enough, then the network will adjust around it. So it really doesn't matter. You can add any vector into it, just so long as it doesn't overwhelm the actual learning. Nothing will happen. Gap. Okay, what is the gap? The gap is how far it is from 0. Gap. Okay, gap equals source, no, outputs. We take the outputs dot I minus 0. Minus 0. Is it 0 minus or minus 0? Oh, it's 0 minus. We have to make sure we don't get a 0. 0 is the target that we want. And outputs, this gets us how far it is from 0. Okay. Now the gradients. We didn't compute a gradient. Grad. Gradient equals the gap divided by the range. We need a range. Okay, no, not range, range. Okay, what's the range is the standard deviation 1. Gap divided by 1. What's the ratio? Because we're using a ratio from 0 to 1. We take the gap divided by 1 to find out how far it is from 0. How far it is from 1 in a ratio from 0 to 1. The range can be anything, but here I'm just gonna divide it by 1 anyway, just to make sure that it normalizes to 1. Okay, so now we need to find out how we're gonna fix it. Okay, so we have to square it. The reason we're squaring it is the same. It's when you see the formula for this, you see something about a log, but I'm not gonna bother with this. It's just too tedious. So we're just gonna square it. The reason we square it is to create a parabola, and the closer it is to 0, the smaller this value. The farther it is from 0, the larger this value is going to be. Okay, so it's the gradient is the gap squared. Okay. Okay, the farther it's from the target, the largest number is going to be. So this tells us what you need to do here. Okay, next step. We need to figure this out. Be very careful how we do this. Okay, result. Okay, we need the deltas. Okay, source is the deltas here. Okay, we take the source. We take the source. Now we need to figure out what we're doing here. Okay, this is a bit complicated, so I'm trying to figure out if I'm getting it right. Source equals. Okay, source equals source. Source here is the backpropagated gradient. The reason I put it here because this function already passes the gradient, so I'm just going to use it as a placeholder. But later we're going to make its own function. Okay, source times. Okay, we take the gradient. No, it's not times, it's plus. Source plus, we take the gradient. The gradient here times a learning rate. It's not the main learning rate, it's just a learning rate that we choose ourselves. Okay, 0.01. Now let's make it 0.01. This is important that you choose something very small here because you do not want it to overwhelm the source. It should only activate when you're very far away from the target. If you're close to the target, it should do basically nothing. So that's why we square it here. We square it out here to get a number that's between 0 and 1. The farther the larger it is, well, it just gets really big. If you go far from 1, or far from -1, it gets really big. Then we multiply it by 0 1 to get our gradient, and then what else will you do? I'm trying to remember what it is. Okay, so it's multiplied by the delta. Okay, gap is the delta right here. Okay, it can be negative or it can be positive. Oh wait, we can't just do it like that. Is it like that? Target minus hub. Oh, we have to take the absolute value. Oh, we need to take the absolute value here. Oh, really? Do we? Huh. I'm trying to figure out if we're supposed to take the absolute value. I think we're supposed to. Yeah. I haven't done this in a while, so I'm not really sure how it goes here. So gradient gaps. No, it says with squared it becomes Oh, I keep forgetting this thing. I'm not thinking. We don't need the absolute value here. Gap. Okay, so the gap can be positive or it can be negative, so it doesn't matter. That's why we do here. We don't need the absolute here. So we multiply it by the gap. What do I call it? Gap. This is the gradient. Okay, this is the level. Okay, I'm trying to review this here. The gap is the difference between the output and zero and in the target, which is in this case is 0. Okay, the gradient is the gap squared. So the farther it is from our target, the bigger it is. And now we get the gradient times the learning weight times the gap right here. And that's it. This should be enough to fix the problem. So the farther it is from 0, the more you push it back towards 0. The closer it is from 0, the less you do. Okay, this should fix the problem. So let's rebuild. I'm going to rebuild and see if it works. And it seems to work. I mean, it's not working very well, but something is missing. But it's better than it was before. Okay, we're still using the momentum optimization here. So that's why it's not working too well. But the momentum optimization is not great compared to Adam optimization. But compared to what we had before, it is working very well. It fixed the problem. And let's review. Yeah, you take the difference between that and 0, and you find the ratio between that and this. Gives us the standard deviation, the distance from the mean, the standard deviation times 1, the ratio between the mean and the standard deviation, and multiply by learning rate. And well, it's definitely not the right way to do this. Like, I'm not saying this is the right way to do this. This is absolutely not the right way to do this. But it gets you the basic idea. You just take the vector and then add a new vector to it to get it to nudge it to where you want. Like if you're doing like if you're making a variational autoencoder, whenever you see any equation, that's all it's telling you right here. All it's telling you is add a vector to the gradients to get the. You can think of all the points in the hidden layer as a in the latent space as a point in space, and then you push in the points where you want them to go. You can just add whatever you want to the gradients, and then you just push the points to wherever you want to go, and the learning will work. So you don't really have to worry about it, and it's working. Let me just test the other one and make sure it's the same. Okay, we're gonna try from momentum to add a grad, see if it works better. And it's compiling. It's gonna take a few seconds here. Let me just pause. And it's working too. Again, it is not working anywhere near as well as the Adam optimizer, but it is working. Slowly, step by step, it's working. Okay, always on top. Okay, yep, it's working. Let's try the other one. Let's try Adam, make sure it is the same. And run. Okay, this one's working also, but it's not working as well as it did before. So maybe I'm doing something wrong. I'm going to try to apply corrections, see if I can get it to work better. Maybe the gradients are just too big. But anyway, it fixed the problem. I'm gonna try making some adjustments, see if I can improve on it. Okay, this is as good as I'm ever gonna get. So now I'm gonna translate this into an actual function. The question is, what do I call it? Let's call it transfer. Transfer something. Okay, we need a way to make sure this works perfectly. Whoa. What is that? Okay, transfer. What's the name I'm gonna use? Transfer. Whoa. Okay. I'm messing myself up here. I'm getting lost. Okay, transfer. What's the word? Transfer focus. Yeah, focus. Focus. Why focus? Because the goal is to get the gradients to focus in one spot in the center, towards 0. Okay, now we need we can't simply add everything the way it's supposed to. Just result source. Gonna focus result source target. Okay, now we need to define the parameters here. Result is the output deltas. Source is the parent deltas, the deltas in the outputs, and the outputs. Well, that's the outputs, and now we need a target. Normally we use 0, but 0 isn't always the right target. So target is the mean. We have mean and standard deviation, but target is just the mean point in the latent space. It could be anything. What else? We have the length. There's something else we're missing here. Mean and standard deviation. Okay, what do I call it? Okay, length. CUDA null unit length. Oh, stop it. Now this thing's being difficult again. Okay, CUDA null unit length and the mean and standard deviation. Target is the mean. Now we need a standard deviation. That's what they're called, mu sigma. Mu and sigma is the learning weight. It's not a learning weight. It's just well, the documentation calls it mu and sigma, so I'm just gonna call it mu and sigma. Okay. Okay, right here. Having a small screen just makes everything so much more difficult to read, so I'm just gonna move everything down here like this. It just makes everything easier to read. Okay, get rid of that. We don't need that. Okay, CUDA null unit gap and gradient. Grad target. Now target. Target.I minus the output.I. Target.I minus output. Oh wait, no, we don't. Why do we need a result? We don't need a result. Okay. Result. Just gonna follow the normal pattern. Result is the second up. Because we're doing everything backwards here. Transfer focus reverse. Transfer focus reverse. There's no focus forward, but we need to call reverse just so we know that everything's being reversed from source. Now from result over to source. It's copying from result to source. That is to make sure everything's clear. Okay, gap divided by mu. Calling it sigma doesn't really tell me what it means. Range. Let's say lambda. Using Greek letters for this is really not a good idea. Okay, range. Range is standard deviation. Standard deviation range. No, CUDA new unit. It's a number, not a pointer. Range. Target minus output. Gap divided by range divided by 1 to get a normal value between 0 and 1. And gradient times lambda. Lambda is basically the learning rate. How fast we're supposed to move based on the gradient. Yeah. Okay, find out how far it is from the target, and then move in a parabola over to down to 0. The farther it is, the more you push in. So the goal is to just to get everything to be as close to 0, but close to the right range without pushing too much. We cannot push too much. Just that's the important part. If we push too much, we're just gonna break the learning. Okay, now you have it. Focus reverse. Transfer focus. Calling it reverse doesn't really make sense here. I'm just confusing myself with the names. Okay, let's make sure we have everything here. Okay, now we have range, outputs, targets, target, not target, target, and CUDA null array, lambda, and range. Whoa. Oh, it's messing me up. Target, lambda, and range. Oh, we don't need transfer. Everything's messed up. Doesn't matter. Outputs, let's just add this here. Range, outputs, target. This just, why do I keep misspelling this? Target, output, range. Okay, make sure that all the arrays are the same size and that they're not 0. I keep misspelling this. Target up, and all the arrays the same size, everything's the same. Range, transfer focus. Now focus. Let's just make sure you don't mess the names up. Now focus. Transfer focus. Target, lambda, and range. Okay. Outputs. Result. You don't want to get this wrong. Target. Okay. Lambda. And range. Range is how far you are from 0, and length. Did I miss something here? Yep, I probably did. Yeah, I did. Okay. This tells us to focus. Okay. This is a lesson to learn. This is not the only thing you can do with the gradients. Basically, if you have several categories, you can adjust them into different spots simply by pushing them into whatever region you want them to be in. They don't have to be in the center. Okay, just pick a spot and then group them together where you want. You can manipulate the latent space any way you want here. Okay. Crap. Okay, lambda range. Let's just copy it into our library and focus, not transfer reverse, transfer focus. And no, that's it. No. Okay, transfer reverse, transfer focus. Okay. Now let's rebuild. Let's just make sure we have everything right here. Come on. Okay. Now let's go back to neural network. Layer bias. Let's create a new file. It's getting tedious, but I think it's mostly necessary just to get everything to work. Visual C++ editor file. Let's copy everything bias. Bias, focus. Now we're creating a focus layer. This is the equivalent of a batch normalization, but batch normalization is just way too complicated, so this is just a substitute. Okay, focus. Focus create. Okay, to create focus, you need mu and sigma. Lambda. Wait, what do we need? Okay, lambda and range. No. Is it CUDA null unit? Yeah, CUDA null unit. Range, not pointer. Come on. It's not liking something, but I don't care. Okay, focus. Type null layer focus. Okay, layer. Okay, yeah, we'll do that later. Okay, we don't need gammas, we don't need vectors, we don't need weights. It's just something. We don't fill 0, we don't need any of that. Okay, bias feed forward. Here we just need copy. Okay, lambda feed forward. Now focus. Focus feed forward. Oh, there's something else we need. We need it right now. It cannot wait. Okay, null layer. Add this focus. Okay, layer CUDA null unit. No. CUDA null unit layer value 1. We're gonna need another value later, but it doesn't matter. Okay, now layer value 1. Okay, focus feed forward. What do we need? No copy. Next to the outputs, parent to the outputs. We don't need weights. What is it complaining about? No, something's missing. I don't know. Layer focus create. CUDA null layer focus create. Doesn't matter. Feed forward. Copy. Outputs. Layer bias back up. No, focus back propagate. Maybe I'm missing something, but I don't care. Okay, we'll figure it out later. Okay, now we need this. No, transfer focus. Copy and paste. Transfer focus. Oh, there are two values. Ooh, now I remember. Parent layer value 1 and layer value 2. Oh, we need to make sure we don't forget this. Lambda and range. Range. I'm still missing something, but layer value 1, layer value 2. Okay, this part is done. Okay, no copy here. Transfer focus. Okay, parent.deltas. That's the result. Wait a minute, is that result? No, we have to. This is where we can get into trouble. We have to reverse this right here. Next dot layer value 1. That's the result. Parents dot layer deltas. Next. Parent. We just copy. I don't want to type this every single time. Parent dot layer deltas. Parent dot layer. Need to make sure we get everything right here. Okay, result, source, outputs, and target. Ooh, outputs. And target. What is target? Target, we have to pick another array. Alphas. That's what usually enforce. No, alphas. PH files. Okay, so you have to create this. I thought we needed, but apparently we do. Create layer something and fill it with 0. Create layer focus. Create gammas. Let's choose alphas. You can use those arrays for whatever you want. It doesn't matter. Only the outputs, weights, vectors, and deltas are really universal and they have to be used for a specific thing. Actually, just the outputs and the deltas are necessary. Everything else can be used for whatever. Alphas. There's no update to it. Distro alphas. I can't type. Okay, couldn't neural focus. Next to the parent deltas. Next to the outputs. No, parent to the outputs. Ooh, let's not get this wrong here. Parent to the outputs. That's the output layer. Alphas and parent dot layer value 1. Parent dot layer value 2. And is that it? Outputs, targets, yeah. We need range. Okay, I'm still missing something, but I can't really figure out what it is. Oh wait, we have to save, that's why. Type library. Is it type library? Yeah. Okay. Type CUDA null layer focus. Let's call it a focus layer, which is our equivalent of batch normalization. It's not a good equivalent, but it gets the job done. Okay, everything's the same. Everything's good. It looks good. But layer value 1, create alphas. Null network. Okay, now let's go back to where we were. Okay, replace transfer. Okay, let's just copy and paste because I don't want to do this every single time. Oh wait. What is that? Why isn't it accepted? That's because it's not part of the neural network yet. Okay, replace transfer with focus. Focus, depth, CUDA neural unit. In what order are they? Let's not miss that one. Let's not miss that one here. Lambda and range. Okay. Lambda. Lambda is how fast we're going. How much to move just so we don't overwhelm the learning. And range. Range. Okay, so that's good. Next. Oh, we have to add in the list. Otherwise, it will not work at all. Transfer. Transfer. Whoa. Oh, not transfer. Oh. Focus. It must be. I must be really tired tonight. Why does it all work? Couldn't do unit. Parent width, height, parent width, height, depth, lambda transfer. It's not liking something. Couldn't null unit. Focus create. It's really not liking something here. Type neural network, add layer focus. It hasn't been defined yet. Oh, add layer null, add layer bias, add layer transfer, and just copy it. Add layer focus. Just copy it. I'll have to do this several times. Add layer transfer, add layer focus. Okay, so it works. CUDA null layers, type null layer layers. Wait. That's not. Just typing problems. Okay, add null layer and add layer focus create. Focus create. There's something else we need to change. Let's just change it now because I don't have to deal with it later. CUDA null layer is equals. Actually, it doesn't really matter, does it? Layer value 1, transfer reverse, parent layer value 1. Well, it's not complaining, so I'm not going to change it. Whoa. If it complains, we'll change it, but for now, it doesn't matter. Okay, lambda and range. Add layer focus. Okay, next. CUDA null layer. Focus. Have to do everything in the right order and in the right way. Focus, feed forward. Focus, back propagate. No, oh. Focus, back propagate. And there's no update weights in either one of those. So, and now focus. Oh, come on. What the? Oh, why does it do that? Focus, destroy. Focus, destroy. Okay. It doesn't like it. Why? Focus. I forgot to rename it. Focus, destroy. Yeah, now it's good. Okay, now let's go back to our source and get everything to work. Okay, transfer, focus. Just add a focus layer after transfer. Is it after transfer? Oh, it has to be before transfer. Focus. Range is 1. No, lambda is 0.01. Not 1. Range is 1. Standard deviation of 1. Okay. As a rule, the focus has to happen before transfer, because we're passing the derivative into convolution and into the bias and convolution. So everything has to be in the right order. Okay, 64 by 64 by 32. Okay, I haven't explained this part yet, how the network is designed, but we'll do that after. (64 by 64 by 10). And bias, width, height, and depth. Okay, am I missing anything? Okay, step 1, let's test this. First we build. Make sure I didn't miss anything. I'm gonna check for all the small errors. I'll be back. Yeah, it did complain. So here, layer value 1, I have to convert it to unsigned long. But other than that, everything seems to be working fine. I'm just gonna correct some small cosmetic stuff and I'll be back. Okay, we fixed everything here. And we still have exploding gradients. Like here I'm using here. You see it's very, very bright. That's because the gradients are still trying to go out of bounds. But because of the focus layer, eventually it fixes itself. The gradients are still way too high right now. But step by step, it should push it back down to something decent. Okay, you can see right here it's working. It's not working very quickly, but it's working. This is a very low learning rate, not very fast, and no optimizer. We're just using basic momentum instead of with an optimizer. So far, yeah, it's pushing in. This is the slowest version. I'm doing one step at a time, so that's why it's taking so long. But eventually, if you let it run long enough, it should correct itself. If you had a bias, this would go a lot faster. But here I'm not using bias, just the basic convolution. So that's focus layer for you. It's just a way to push the gradients back towards zero. If they go too far out of bounds, it gradually pushes them back to zero. You can set the target to whatever you want. Like if you have two different categories, you can use a similar function to separate the values into two different groups. The thing to remember is not to push too hard if it gets too close, because otherwise the learning simply will not work. Okay, I'm looking at it here and it is working. It's just gonna take a little while to train because training a neural network takes time. So other than that, it's working. So right now I'm using very small neural network with just one or two layers. But because we don't have to worry about exploding gradients anymore, we can make the networks a lot bigger now. So this is a good thing to know. Oh, just remember, the focus layer goes after convolution and bias, and after matrix and bias, but before transfer layers. It's just supposed to normalize the gradients. But it works. It fixes the problem. Item optimizer and bias will work better, but even without them, it still works. So that's it for today.